Hello everybody. So today what we're going to be looking at is proofs using angles. Now in order to do proofs with angles, we first have to remind ourselves about a few special angles that we tend to get confused. Even I do sometimes. So let's start out with the definition of a few special ones, like vertical angles. Now vertical angles are opposite angles formed by intersecting lines. So if we're looking at this picture here, I have marked a pair of vertical angles. So we can see those intersecting lines. The vertical angles are going to be here with 1 and 2 because they're opposite. And we also have another set of vertical angles formed here, here, and here that would also be a pair. So any intersecting lines are going to form 2 pairs of vertical angles. We also have what's called a linear pair. Now you might notice the word line in there, and that's because a linear pair forms a straight line. It's just 2 angles that together will form a straight line, and they will be adjacent because they're going to share one of those sides. As you can see here, 1 and 2 would be a linear pair. Now these become really useful when we start doing proofs. So we have on our theorem sheet a few proofs to do with angles, and I did them in a different color to help you pick them out at a quick glance. You can even see that on the front we have that with the angle addition postulate, again that slightly paler color. When you are trying to do proofs, this is your friend. You want this out so that you can make sure that what you are concluding actually is covered in the theorems or in the definitions. So let's start with angle congruence theorem. Now angle congruence theorem is just like our segment congruence theorem, only this time we're going to be talking about angles. So remember, our segment congruence theorem basically lets us switch between congruency and equality. And remember, congruency is always talking about the figure, like a line segment itself, whereas equality is always talking about its measure, like the number 5 or 5 inches, as opposed to the actual AB, which is a drawn line. Same thing is true of angles. Angle 1 would be a physical angle that you can draw. Measure of angle 1 is the number that you get when you measure it, like 14. And it's just saying, again, in angle congruence theorem, you can switch between congruency and equality. And back again if you would so desire. Please watch, equality does have the little m in front to tell you it's a measurement. Now let's get into the ones that can help us with formulas. Watch out with linear pair theorem. Now, if you know that something is a linear pair, so it forms that straight line regardless of how they are set up, what you're going to be able to assume is that those angles are supplementary. So a lot of times we'll be able to say, using the linear pair theorem, that angle 1 and angle 2 are supplementary. Now please watch out. The linear pair theorem does not give you an equation. It only tells you that they are supplementary. Now you can use that information later on when we use the definition of supplementary, but this theorem itself has no equal sign in it. It's just a step to get you a little bit closer to the equation that you want. So let's look at the definition of supplementary, because if we know that they're supplementary, well, what does that actually tell us? Well, it tells us if an angle is supplementary, then the measures add up to 180, and vice versa. If the measures add up to 180, angles are supplementary. They can be attached like a linear pair, or they can be separate. Doesn't matter so long as their measures equal 180. And the definition of complementary is really similar to that. In that one, if an angle is complementary, or if 2 angles are complementary, the measures are going to add up to 90 degrees, or if they add up to 90 degrees, they are complementary. Again, they do not have to be attached in order to be complementary, though traditionally we do see them like this with the little 90-degree mark in the corner. Last theorem that we're going to talk about today is the vertical angles theorem. And the vertical angles theorem tells us that vertical angles are congruent. Now, you've already seen what a vertical angle is. It's the angles that are opposite formed by intersecting lines, so 1 and 2. So those 2 are vertical angles, therefore you'll be able to conclude that they are congruent. Please watch here, you do have congruency and not equality. So in your proof, you might have to go a step further so you can get it into equality using the angle congruence theorem. But I like to keep my theorems that are going to give me equations highlighted, because remember that those are going to be used quite frequently as we try to switch our questions into algebra. So this one gives me an equation. This one gives me an equation. This one does not, right? It just leads me to an equation later on. And this one's going to give me a congruency statement, so I'll be able to turn that into an equation later on. Those are our rules. Now let's see what we can do with them. For our first proof, we've been given this picture. And we want to find the measure of DBC and prove that we have it right all the way. So I'm going to start with my givens. Now what we've been given so far is the picture. I'm going to allow you to also say in your givens if you can spot any vertical angles or linear pairs. You can't really tell something supplementary or complementary unless something directly tells you, like, hey, this equals 90, like this little symbol in the corner does that. Or, hey, this is 180 degrees, and that's literally in the givens. The only things that you can tell from a picture are really going to be that linear pair. You can assume this is a straight line, so these must be a linear pair. And you can also assume vertical angles from a picture because it's just intersecting lines, so you'll always be able to assume that. And since I can say that these form a linear pair, I'm just going to do that right now. A, B, D, and angle DBC are a linear pair. Technically, that is the definition of linear pair, but I'm going to allow you guys to put it underneath givens. Notice I'm also given some angle measures, so I might as well list those. The measure of angle ABD is going to be equal to 7Q minus 46. Whereas the measure of angle DBC is going to be equal to 3Q plus 6. So I have all my givens down. Now what I want to do is I want to form an equation. And when I look at this, I can see the equation. I can even kind of work it out in my own head. I know that I'm going to add these two angles together to get 180. And I'm going to actually skip a spot for that so I can fill something in just a second. I know that these two angles add up to 180. ABD plus DBC is equal to 180. Now I know that because I know that they're supplementary, right? When we're looking at this, you can kind of see they're going to add up to 180 because they form a straight line. But when I use the definition of supplementary, which is the one that gives me that 180 formula, right? If I look over here, that's the one attached to supplementary. I don't actually have the word supplementary mentioned, so nothing in here has been directly stated as supplementary, which means I can't technically use the definition of supplementary first. So I'm going to have to say that those two angles are supplementary. So angles ABD and DBC are supplementary. Now the question is, how did I know they were supplementary? Well, I told you I knew they were supplementary because they formed a straight line. In other words, because they were a linear pair. And so I'm going to look for the word linear pair, and I see the linear pair theorem, which says that if they're a linear pair, then they're supplementary. So that's perfect. I know if they're a linear pair, then they are supplementary, so that is the linear pair theorem. So be careful here, because most of the time we want to jump directly to this where we're giving our equation, and unfortunately we do need a separate step to make sure I can actually use the definition of supplementary. And it's always a good thing to check that, hey, if you use supplementary, you've mentioned they're supplementary. If you use something like linear pair, have you said above that they are a linear pair? If you can check that, that will confirm that you are able to use these sorts of theorems, and it can save you a few points. Okay, well now I have my formula, so I know that I'm going to be able to do some substitution and get fully into that realm of algebra that we so enjoy. So I'm going to fill in the formula, keeping it stacked very neatly so that my DBC is right underneath DBC, and same with ABD, and that's substitution. Next, I'm going to simplify this side. So I add together my Q's, I combine my normal numbers, or constants, I suppose, and I'm just going to note that this is simplification. Here I start solving for Q. I'm going to add 40 to both sides, which is going to give me 220. And since I'm adding to both sides, that is the addition property of equality. Next, I'm going to divide both sides by 10, which gives me 22. And since I'm dividing and multiplication and division are the same thing, mathematically speaking, I end up with the multiplication property of equality as my support. Now, the thing is, I want to stop, but I'm not actually done because what I need is the measure of DBC. But I said above that the measure of angle DBC is equal to 3Q plus 6, which means I should be able to write 3 times, well, whatever my Q is, 22, plus 6 instead. And that's substitution, because I've substituted in a value for Q. Last but not least, I do need to simplify it. Don't leave your reader with that work. 3 times 22 is 66. Plus another 6 is going to give you 72 degrees, which would get us all the way to our final answer. We know what DBC is. And since what I've done is combined terms and done some basic algebra, we're just going to call that simplification. In our second proof, we've been given this picture, and we're told to find x. Now, I've already filled in my givens, and you might have noticed that I talk about angles 1 and 2 and the measures of 1 and 2. This didn't actually give me labels, so what I've really done here is I've labeled this one angle 1 and labeled this one angle 2. And you're allowed to do that. That's called like making auxiliary marks. You're adding in a few details to make it easier to talk about, like your own sort of slang with whoever has this picture as well. So I'm allowed to do that. I have that they are vertical angles because I can see that these two things form a vertical angle, and that's one of the two things I'm allowed to just note given a picture. And that means I can start my proof. Now I know that I want to say that vertical angles, tell me a little bit more. And according to this, vertical angles theorem tells me that the angles themselves will be congruent. Now be careful here. I know that angle 1 is congruent to angle 2 according to the vertical angles theorem. I cannot jump right away to an equal sign because the vertical angles theorem only tells me congruency. But thankfully, we have something to help with that. I can switch out of congruency and into equality using the angle congruence theorem. So that's what I'll do in my next step. And since I'm switching into a measure with equality, I'm going to include the little m in front of the angle sign. So I know I'm talking about the measure of the angle. So this is the angle congruence theorem. Please watch that you don't use segment congruence. We are not talking about segments here. So at this point, I can substitute. I'm going to substitute in x plus 16 for measure of angle 1 and 4x minus 5 for measure of angle 2. Here, I'm in the realm of algebra. Subtract x from both sides, and you get 3x on this side, and while I'm doing my addition and subtraction, I might as well add 5 to both sides to get 21, and that is the addition property of equality. Here, divide both sides by 3, that gives you 7 is equal to x, according to the multiplication property of equality. And we don't like to keep the x on this side. We really want it to read x equals 7. Even though it doesn't directly say that, your x should always come first. And since all I've been doing is flip-flopping, that is the symmetric property of equality. This time I don't need to substitute back in and find an overall angle because all I'm looking for is x, so I would actually be done. I would like to remind you that I'm really familiar with these theorems and these properties, so when I'm going through this, these things pop into my head right away. However, when you're going through these, you need to slow yourself down. You need to look up the properties and double check that they're allowing you to do what you think they are. Because a lot of times we end up skipping steps if we don't reread the theorems, like this vertical angle step, or if we're looking earlier, like the linear pairs theorem when you just jump right to supplementary. So please take your time, reread things, and don't be afraid to stare at your sheet for a little bit. That's unfortunately the time-consuming part of learning, giving yourself a break so you can find all the information necessary. Now your homework is posted on Classroom, and let me know if you have any questions. You do not have proofs for today's homework. That will come with tomorrow's. Have a good night.